All right, J-Wars, buckle up. We're diving into one of the heaviest hitters in organic chem, alcohols, phenols, and ethers. Look, this isn't just some chapter you can skim. This is a real battleground where ranks are made or broken. So, let's cut to the chase and get straight into the strategy.
So let me ask you something. What's the real difference between just knowing your chemistry and absolutely acing it? It's not about memorizing more stuff. The answer, my friends, is strategy. And that's exactly what we're going to crack open today.
See, anyone can memorize the rules, right? That's just knowing the reactions. But knowing the game, now that's different. That's about getting inside the examiner's head, seeing the traps they lay for you before you even get there, and knowing exactly how to sidestep them. Today, we're not just studying, we're learning to play the game.
Okay, so welcome to your strategy session. Think of this as our exam cracker briefing. We're going to laser focus on three things: the reactions that show up all the time, the classic traps that trip everyone up, and the shortcuts that are going to save you those crucial seconds on the clock.
All right, first things first. Let's talk about the absolute must-knows. These are the big ones, the reactions that pop up so often they're basically free points. If, and that's a big if, you've got them locked and loaded in your playbook.
So let's kick things off with a total classic, the Reimer-Tiemann reaction. And listen, don't just memorize the name. Think of it like a specific tool in your chemistry toolbox. What's its one job? Simple. It takes phenol and reliably turns it into salicylaldehyde.
And here it is, laid out perfectly. You've got your starting players on the left, phenol, chloroform, and a strong base. And what do you get? Salicylaldehyde. But, and you got to pay attention here, here's the detail the examiners love to test. You actually get two products, ortho and para. But the one you need to remember, the major product, is the ortho one. That's the money shot right there. Don't forget it.
All right, next on the hit list is Kolbe's reaction. This is another one the exam setters are just in love with. This is your go-to play when the goal is to get salicylic acid from phenol. See that? Same starting point, phenol, but a completely different result.
So how does it work? It's basically a three-part play. First, you hit the phenol with a base. Why? To make it a more aggressive attacker, the phenoxide ion. Then, that phenoxide goes after carbon dioxide. And finally, you add some acid to finish the job. Boom, salicylic acid. Just burn this sequence into your brain. Base, CO2, acid. Got it?
Okay, you've got the core plays down. Now for the really fun part. Let's talk about the traps. This is where we learn the enemy's tactics, because knowing what they're going to throw at you is half the battle. Seriously, this is the inside info that separates the good from the great.
Okay, check this out. You see a question like this on the exam. A secondary alcohol plus HCl. Your gut reaction, your instinct, is probably to just swap the OH for the Cl, right? And you'd pick option 4. And that's the trap. That's exactly what they want you to do. The real major product is option 1. So what the heck is going on here? It all comes down to one super important idea.
And here it is, the secret weapon they use against you, carbocation rearrangements. See, that reaction goes through a carbocation intermediate. And here's the role of the universe for carbocations. If they can become more stable, they absolutely will. They'll shift things around to get to a better spot. I'm telling you, this is probably the #1 most common trap in this whole chapter. You have to be on the lookout for it. So how do you spot it and beat it every single time? It's a simple 3-step checklist, okay? 1, make your initial carbocation right where the OH group left. 2, stop and look next door. Check the adjacent carbons. Ask yourself, can I make a more stable carbocation here? 3, if the answer is yes, you do a shift, move a hydrogen or an alkyl group over. After that, and only after that, do you let your nucleophile attack. Follow those steps, and you'll never fall for it again.
All right, so you know how to spot their traps. Now, let's give you the counterattacks. These are the patterns and shortcuts that will let you fly through these problems while everyone else is still scratching their heads. This table right here, this is your ultimate cheat sheet for reactivity. Seriously, burn this into your brain. The logic is simple. For anything that involves the carbocation, we're talking SN1, dehydration, the Lucas test, it's all about stability. So tertiary is king, then secondary, then primary. Easy. But for SN2, it's the exact opposite. SN2 is all about sneaking in for a backside attack, so bulky groups are a no-go. That means primary is the fastest. Get this logic down and you'll be solving these questions in seconds. Okay, I want you to remember one number. Just one. 1 million.
Why 1 million? Because that's roughly how many times more acidic phenol is than ethanol. You look at their pKa's, right? Phenol is around 10, ethanol is around 16. That little difference of 6 on the pKa scale is actually a factor of 10 to the power of 6. That's not a small difference, that's a massive gap, and it explains almost everything about why they react so differently.
Now, this is a classic pattern you have to recognize instantly. Look at this. In both cases, we're reacting phenol with bromine. Same stuff, but look what happens when you change the solvent. It completely changes the entire game. You use water, a polar solvent, and bam! The phenol gets so fired up that you get this tribromo product like instantly. But if you switch to a non-polar solvent, like CCl4, you can tame the reaction and get just a single bromine to add on. The takeaway? The solvent isn't just a detail, it's the director of the whole show. Always, always check the solvent.
Okay, we're in the home stretch now. Let's pull all of this together into one final super fast briefing. This is your 60-second cheat sheet, the stuff you look at right before you walk into that exam room to get your head in the game.
Okay, alcohols, what do you need to know? Prep, you got your Markovnikov and your anti-Markovnikov. Done. Test. Lucas test. Remember, 3 degree is fastest. The absolute biggest trap, watch out for that carbocation rearrangement. And finally, oxidation. PCC is your magic wand to stop at the aldehyde.
Next up, phenols. Key fact, way more acidic than alcohols. The 2 named reactions you have to know, Reimer-Tiemann and Kolbe. Don't forget the bromination trick. It's all about the solvent. And here's a sneaky little trap. It's acidic, sure, but it's not strong enough to react with sodium bicarbonate. They love asking that. And to finish it off, ethers. Your #1 prep method is Williamson synthesis. Remember, it's SN2. If you need to break an ether, you bring out the big guns, hot, concentrated HI or HBr. And now for the golden rule, the biggest trap for ethers. If you have an aero group attached, it never, and I mean never, becomes the halide. It always turns into phenol. Lock that in. So there you go. You're not just someone who knows the rules anymore. Now you know how to play the game. You've got the playbook, you know the enemy's traps, and you've got the shortcuts to beat the clock. So now the only question is, when you see one of these traps on your exam, which one are you going to smile at because you know exactly what to do? Now go get them.